So Faraday's law states that the induced EMF, the magnitude, the size of that induced EMF across the end of a conductor is directly proportional to the rate of change in magnetic flux linkage with the conductor. So we know this, I won't spend too much time. We know that the formula of the induced EMF, it is equal to negative N, right? The change in magnetic flux divided by the rate or the change in time, or delta T. Now, many people are saying that, are asking me, why is our formula has a negative? Why negative N, the change in magnetic flux? Please answer me in the comment section. Why do we have negative N delta phi divided by the change in T? I won't continue if you guys don't answer me in the comment section. Why do we have a negative? Why? Morals, Sensei, wherever you are. Why do we have a negative in front of our formula? Why? So flopo for negative run the regis, right? So the reason why, the main reason why we have negative is because the induced current, or that induced EMF, it opposes our magnetic field as well as our magnetic flux. The reason why we have a negative is because that induced, remember when we say something is being induced, is being created. So it simply means that the voltage, the EMF that is being induced, that's been created, it opposes the direction of the magnetic field as well as the magnetic flux. It opposes the direction of the two. Are we clear? Let me continue. Document. The thing is, I don't know how to use this, but please mute yourself, because if you don't mute me, I'll be hearing sounds. Please mute yourself. Okay. We were speaking about the reason we have a negative. It is because it opposes the change in flux. What is the flux? The magnetic flux, and also the magnetic field. Then the E stands for the induced EMF. So if you're being asked to calculate the induced EMF, you are going to calculate this small e over here, which is equal to negative N multiplied by the change in magnetic flux divided by the change in time. The change in flux, remember the symbol delta, this triangle simply means the change. I don't know how to draw a triangle, but I will try. So the change in magnetic flux. I'll explain what the magnetic flux is as we continue. Then this capital letter N stands for the number of loops or the number of turns. The examiner can use the word loop or can use the word turns. right? So don't be confused. Loops and tens are one and the same thing. Loops or tens. Sometimes the examiner can say we have 200 tens. Tens simply means one and the same thing. I don't know how to write. Please be patient with me, the number of tens. Let's continue. The EMF has a negative sign because it opposes the change in flux. I've also forgot to include the magnetic field. The magnetic flux is the product of the component of magnetic field, that is B cos theta, and the reason why we are using cos, not sine, it simply means it is a horizontal component of the magnetic field, which is perpendicular to the surface, and that area, which is capital letter A of the surface, the field passes through, right? Very much important. Then our magnetic flux. You need to be very careful when you are doing physical sciences. If the examiner says calculate the magnetic flux, you use this formula. But if the examiner says calculate the change in magnetic flux, you are going to use the first formula, base formula, first one. You use it if you are being asked to calculate the change in magnetic flux, and if you are asked to calculate the magnetic flux, you use this formula, because delta means the change, and in this formula we don't have delta, but in this formula we have what? The delta in phi. That Greek symbol stands for phi. So I have given you the formula of calculating the magnetic flux. Let's look at each and every letter, what it represents. So this B stands for your magnetic field, which is measured in Teslas, right? Which is measured in Teslas. If you are given a question and they say this coil has got 20, then they say T. This T simply stands for what? For Tesla. That is your magnetic field. That is your B in your equation. Then we then look at A. I want you to listen to me very carefully with A. A is the area in which the magnetic field passes through. You see, from this picture that I've given you, you see this is your A, this is your A, this is your A, right? So, you must look at the statement, read it with an understanding. The time is ahead of us, but let's hurry up. So if they say it is a circular coil, the area that you're going to use is going to be the area of a circle. If they say it is a square coil like this one illustrated on this picture, the formula that they're going to use is what? L multiplied by B. You can say LB, or rather L squared, but you must be careful with the area that you are using. You cannot use the area of a circle, provided that it is a what? They told you that it is a square coil. So if it is a square coil, you use the formula of what? Of a square. Let me erase over here. Now, another thing that I believe we're going to fight when it comes to is theta. This theta over here, it is the angle between the normal. Look at here, they've illustrated normal to A, they've shown normal to A. You see this dotted lines, it is the normal. So we are looking at the angle between the normal and what? And the coil placed. Look at if they place, remember this blue board, this brown board over here is your what? Your magnetic field, magnetic field of the coil. So if they say that, remember the theta is the angle between the normal and what? And the coil. So if the examiner says that we put our coil perpendicular to the magnetic field, this blue board over here is our what? Your magnetic field. So if it is positioned perpendicular to the magnetic field, it is going to be like this. Let me use which color? Let me use green, this line. It is going to be like this if it's perpendicular. This is okay. Let me go back. Let me erase over here. So if it is positioned perpendicular, it's going to be like this. So that it is what? Perpendicular to the what? To the magnetic field. But which angle are we looking for? We are looking at the angle between the normal, these dotted lines, and this green line that I have drawn. If you put your protractor over here, you are going to get what? 0 degrees. Meaning if it is positioned perpendicular to the magnetic field, the angle between the two, the angle over here, it will be what? 0 degrees. But if it is positioned parallel to the magnetic field, let me draw it. If it is positioned parallel to the magnetic field, it is going to be like this. Because if it is parallel, it is definitely going to be like this. I'm sorry, that looks awful. Let me fix it. If it is parallel, it is going to be like this. Because it is parallel to the magnetic field. So which angle are we looking at? The angle between these dotted lines, as well as our coil. Which way is our coil? Our coil is over here. So what is the angle between these two? This is the angle that we are looking for. Is what? 90 degrees. 90 degrees. So if the coil is positioned perpendicular to the magnetic field, theta is 0 degrees. But if it is positioned parallel, your theta will be what? 90 degrees. Before I continue more, and whoever who is attending, is there any question? Let me unmute you so that we can start with our questions for the day. Let me see if there is any question so far. Please speak if there's a problem with any. Okay. Where exactly? From the beginning, Mufuna. Okay. You had a problem with the Zoom. Okay, fine. Okay. Is there anyone who does not understand the issue of theta? Why is it 90 degrees and why is it 0 degrees? Fancy malls came off. Let me just go back and okay. Let Mafra also hear the issue of theta. Okay, let me just hurry up because I want us to do the questions. Okay, let me hurry up and go back because I have to do electric circuits. Let me just summarize this whole thing. Firstly, we're going to look at magnets, right? So, if you are being asked to draw the magnetic field lines, remember in the last chapter we've drawn electric field lines, but here we are drawing the magnetic field lines, right? So the principle says that the line will always move from a north pole to a south pole. That is the principle. Are we okay? Okay, let's hurry up. We then have the right hand rule, right? The right hand rule says that the thumb can either point in the direction of the current or it can either point in the direction of the north pole. The thumb, right? Let's look at picture number 1. If you see the thumb point in the direction of the current flow, whereas the curling fingers, your 1, 2, 3, 4 fingers, will point in the direction of the magnetic field. Right? But if we introduce a magnet, the thumb will point in the direction of the north pole, whereas the curling fingers will point in the direction of what? Of the current. So if we have a magnet involved, the thumb is the north pole and the curling fingers is your current. Let's hurry up. So here we are looking at the factors which affect what? The magnitude of the induced current. So my friend, because this is theory, I'll just send you the notes and then just rewrite them because like it is more of theory. Factors, strength of the magnetic field, the greater the magnetic, the greater or the stronger the magnet, the greater the induced EMF. Then we have Faraday's law. Definition, we can cram it, and we know that E stands for the induced EMF, whereas the change in magnetic flux, this delta phi, stands for the change in magnetic flux, and N is the number of loops or the number of turns, depending on how the examiner wants to give it to you. We then have the principle. You will be asked, why does our formula have a negative? Why is it a negative N, not a positive? The answer is because the induced EMF, it opposes the direction of the magnetic flux, of the change in magnetic flux as well as the magnetic field. That is, you can cram it. Then we have what we call a magnetic flux, which is the product of the horizontal component of the magnetic field, and which is perpendicular to the surface, right? And the area of the surface the field passes through. Now, I'll explain it nicer as we continue. I want you to look at this picture. We have a formula here which says Greek symbol is phi, which is our magnetic flux, right? Which is measured in Webers. Let me just illustrate that. It is measured in Webers, WB, that is your Webers. In another textbook, they say it is a T multiplied by meters to the exponent minus 3, but I prefer Webers. The B in this formula stands for the magnetic field, which is measured in Teslas. So if they given a statement and they say that a coil with 20 T, this T stands for Teslas, and it is your what? Your B in your formula. Are we okay? Ma follow? Okay, let's continue. A, it is the area in which the magnetic field passes through. This brown board here is your what? Is your magnetic field, right? These arrows are called magnetic field lines, but the area in which the magnetic field passes through, it is the area of these brown boards. The lines are the magnetic field which passes through the area of the area in which the magnetic filled lines passes through. So if you have been told that you have a circular coil, you are going to calculate the area of a circle. In this case, we're going to calculate the area of a square because we've got what? A square coil. Then theta, very much important in my phone. Theta is the angle between the normal as well as what? The coil placed. So the normal, it is this dotted line over here, this one with an arrow, the black one, that is your normal. It is always perpendicular to the surface. So if they say they have placed the coil parallel to the magnetic field, right? If it is parallel, it is going to be like this. Look at my arrow. If it is parallel, it's going to be like that, right? But the angle that you are looking for, it is the angle between the normal, this dotted lines, and also what? The coil. So the angle between will be 90 degrees because we are looking at the angle between the normal as well as our coil. But if the examiner says that this coil is being positioned perpendicular to the magnetic field, it's going to be positioned like this. Let me use a different color. Let me use red. If it is perpendicular to the magnetic field lines, it's going to be like this, so that it forms a 90 degrees over here. But the angle that you are looking for is the angle between this arrow over here and what? And our coil. And the angle there will be what? 0 degrees. This simply means that if the coil is positioned perpendicular to the magnetic field, theta is what? Theta is 0 degrees. And if it is positioned parallel, if it is positioned parallel, theta will be what? 90 degrees. Are we okay? We are fine. Mafuna? Okay. Okay, let's look at these activities before. Let me check, because there are some people who are complaining about not being able to attend with us because of some network issues. We have Juani. Who is Juani? Juani. Okay, fine. Let's continue. So before we go to the questions, let me end the meeting and send you the link again. Is that fine?